Good morning, everyone. Don from Emerson. How are we all doing? Happy Friday. It's Fun Fact Friday. Haven't seen you in a while. Been getting the emails and messages, and I hear you, and I appreciate you reaching out. We've been working a lot of fun stuff here at Emerson. I left you the last time with some CO2 information. We talked about the critical point. We talked about the triple point. We discussed the different peculiarities of CO2. I drew out a transcritical CO2 booster system, as you can see behind me. I tried to fill in as much information as I could. I've got some notes in my hand in case I get off a little bit. But I just want to touch on a few things that you're not going to see in your normal HFC system. Okay, again, this is a transcritical booster, so the first thing you should think about is in the medium and low temperature, there is CO2 in both, and they have shared lines, okay? So they're actually dumping into the same suction header over here. So we have the low temperature compressors, we have the medium temperature compressors, we had what we normally would see as a condenser if we're below the critical point. We've got, I'll talk about this later on. We have what we're going to call a high pressure valve. We have a flash tank, and I'll discuss that a little more. Coming across the flash tank, we're going to have a bypass valve. Down below the saturation tank, the flash tank, we're going to have your metering device going into your medium temperature cases, and then we're going to have a metering device for your low temperature cases, and then back to your low temperature compressors. Again, we're going to have low temperature pressure going in the suction header. We're going to have medium temperature going into the suction header. And we're also going to have this bypass valve going into the suction header if in case it goes above that 87.8 degrees, which is that temperature at the critical point. If we're below the critical point, it's everyday business. We're going to have the condenser is going to be a condenser. It's not going to be a gas cooler. We'll see pressures no greater than what we see in 410A on air conditioning side, okay? So until we get into that transcritical, it's really somewhat common to what we already do, all right? Low temperature will always be in subcritical because it's not going to see ambient temperatures. It's dumping into the medium temperature compressors, okay? So let's start at the medium temperature compressor. Everything above that is going to be critical because it's based on what is seen at ambient, okay? We're above that 87.8 degrees. By the way, remember what I told you the last time. All refrigerants have a critical point. We just don't talk about them. 404A is like 161 or 160 degrees, I believe. R22 or 230 or 134A, pardon me, is 213 or 214 degrees, I believe. So we're not going to see those temperatures realistically on Earth. That's why we don't talk about them, okay? So just wanted to point that out to you. Everything in red is where you're going to see our high pressures, probably somewhere around 1,700 pounds possibly, okay? By the way, our medium temperature compressors can go up, are rated for like 1740 PSIG. The pressure relief valve is going to go off somewhere around 1950, 1958, somewhere thereabouts. Everything in red is probably going to be either stainless steel or some kind of high pressure copper. Again, because when it leaves the medium temperature semi-hermetic compressors, our MT model, our 4MT model, pardon me, that's when we're going to see the higher pressures, if it is in transcritical, okay? So this is a gas cooler. We can't condense the CO2 above the critical point, so we're rejecting heat, but we're not condensing into a liquid. Therefore, there is no pressure-temperature relationship above 87.8 degrees, all right? There's no pressure-temperature relation. I'm going to refer to this as a gas, but technically it's considered a transcritical fluid. But for today, I'm going to refer to it as leaving as a gas. Now, we need liquid to our metering devices, so we need to change this high-pressure gas somehow back into a liquid. And how we do that is with a high-pressure valve. By the way, these are all communicating, and I'll get into the electronics later. I want to keep these videos somewhat short, okay? We have a high-pressure valve. I want you to think about the high-pressure valve almost like a metering device, if you will, okay? So we come through this high pressure. When we drop that pressure down, just like we do on the saturation curve. Here's our evaporator, here's our compressor, here's our condenser in our box, and now we hit our metering device. When we drop that pressure, we go back into that two-phase area, that saturation curve, liquid over here, vapor over here. Anything inside that curve is saturation, okay? All right, we have liquid and vapor. So we drop that pressure. Notice I put it in green now. So we're getting into a saturation area. We've got saturation, we've got vapor at the top, liquid's gonna drop out at the bottom. That's good for us because we need that our metering device. Now, we need to keep this stable. We're gonna wanna keep it somewhere, and I'm just throwing numbers out there. This is gonna be dependent on the OEM, but I'm gonna use the numbers 36 to 38 degrees, somewhere in the tank. With CO2, if it's around 36, 38 degrees, you're going to be somewhere around 521 psig, 521 pounds, okay? Again, that's dependent on the OEM, so don't sketch that in stone. We want to keep that stable so we have a nice solid column of liquid going to our metering devices for our medium temp and our low temp cases, all right? If it gets hotter outside, the high pressure valve's still going to drop that out into saturation, but it's going to get higher pressure in that flash tank. In order to combat that, to keep it stable, we have a bypass valve over there. So if we're dialed in at 36 or 38 degrees or 521 psig, anything above that, the bypass valve is going to open up and release gas into our suction header, okay? So now we have three different pressures going into our suction header. All right, so if it's below the transcritical point, this won't even come into play. All right, so we have a high pressure valve because we need to drop it back to a liquid. We got it back into a saturation here, okay? Liquid at the bottom, vapor at the top, all right? We need that stable liquid going into our metering devices there, okay? Again, there's going to be communication over here. These two are going to be communicating, your bypass valve and your high pressure valve. All right. When we do get into communication, I'll explain to you how that changes over from reading subcooling and how it reads over from the COP on the compressors. And that's a little difference there. And we'll do that for another day. I want to take you back now to some PowerPoints just to show you through this operation, this system, what it looks like on the saturation curve, okay? I'll be right back with you. Hold on. All right, welcome back, everyone. Don here from Emerson. I'm going to finish this up. I just wanted you to see what this looks like on the enthalpy chart. On the left-hand side, we have the system similar to what we were just discussing. On the right-hand side, you can see the enthalpy chart. I wanted you to see this in real time, what they both look like side by side. I know a lot of people don't work with enthalpy charts. I know typically in the field, I didn't. So just walk this around the horn a little bit. So we're going to come through our medium temperature, our 4MTLS models compressor, a semi-hermetic. See the red indicating high pressure gas. We're going to be somewhere around 1700, let's say, 1740, somewhere thereabouts. Okay, coming into what is now our gas cooler, what would normally be a condenser. We can't condense now. We're still rejecting heat. We come through the condensers to number 3. We're up to our high pressure valves. Notice all the controls here too. This is all going to be modulating. We're going to have VFD compressors, VFD fans, our high pressure controller, communicating with our bypass valve and our high pressure valve, case controllers. Everything's going to be going back to our E2, okay? So again, we're back at our high pressure valve. Remember, we need to get that gas, that high pressure gas. It's not a vapor or a liquid. It's considered transcritical fluid. Again, you can see we're in that transcritical fluid state on the right-hand side. High pressure gas, think of that, or the high pressure valve, think of that as a TXV. In this case, it's going to be a CXV for us, okay? Coming through that into our flash tank. Now we have liquid. We drop that pressure. See on our enthalpy chart, we're in that two-phase area again. So now we have liquid at the bottom of the tank, vapor at the top. Come through that to our medium devices, to medium temperature and low temperature. Coming through the metering device in the medium temperature, out through the medium case. Now we come through our low temperature metering device, our EEV. Now we're going to go from the vapor through the flash tank to our bypass valve. outside our bypass valve, so our pressures are getting higher. Remember, we talked about keeping that temperature somewhere around 36, 38 degrees Fahrenheit. At CO2, that would be somewhere about 521 psig. Okay, and this is dependent on the OEM. Coming into our Zoes or our scroll compressor, our ZO, let's say 45K3Es. Something I didn't mention earlier too, and we'll talk more about this at another time, another day. But we're going to want a minimum of 36 degrees superheat at our low temperature scrolls. All right. Keep that in mind. 36 degrees superheat minimum going into our low temperature scrolls. There's our suction header. Notice again, we've got our bypass suction pressure going in there. We've got our medium temp pressure going in there, and we've got our low temperature pressure all going into that suction header. All right. Now, this is a transcritical booster system, a typical system. Okay. When we get into transcritical architecture, we're going to get into some strategies on what that's going to look like. How can we keep that temperature? How can we keep that condenser from not seeing 87.8? Things like ejectors, adiabatic coolers, subcoolers, parallel compression, because those kind of things are going to come into play, because in this transcritical state, if we had 10 semi-hermetic compressors here on the medium temp, at the right temperature, if it's hot enough outside, we might be loading up 5 of those 10, just from bypass gas. So we're going to look at what that looks like, all the different strategies going around the world, and they're closing that gap on that equator all the time. So I just wanted to share that with you, a little tidbit on that. So that's all I had for you today. I hope you got something out of it. Again, I'm Don from Emerson. And again, keep those ideas coming. If you want to see more CO2, let me know. And I will see you in the near future. Probably next week, I'll have another video. I'll keep them coming, all right? Be safe out there if you're on call. Everyone, enjoy your weekend. Have a great day, everyone. See ya. Bye.